Hello, dear students. This is lecture 7 of our series on Introduction to Quantum Mechanics. And today our topic is Postulates of the Quantum Mechanics and Schrodinger's cat. This lecture is going to be very absorbing and interesting because we will, for the first time, give a formal introduction of how quantum mechanics works. So we are going to set up the theoretical framework of quantum theory, and then while doing so, we'll also discuss this cat that you have been seeing on the first slide of my lectures. We'll discuss that what the cat is doing in the box. So let us start. So first of all, how to formulate a theory. So the important point here would be that we'll discuss how to formulate a theory. So this is a very interesting question. In physics, how do you formulate a theory? What are the things that you need to formulate a theory? So we ask a very simple question that what are the basic ingredients that go in formulating a theory? So we ask a very simple question, what are basic ingredients that go in formulating a theory? So this will apply to all kinds of theories that you happen to study in physics. Now, the first step is experimental results. So we have experimental results, new experimental results that challenge our existing theories. The first thing is that you have new experimental results which propose a challenge to existing theories. Now I will give an example here. For example, photoelectric effect. This was an experimental finding that how photons behave, how do photons eject electrons from a metal. The problem was that the existing theoretical framework that should be applicable in this experiment was classical electrodynamics. And classical electrodynamics is not able to explain this phenomenon. So we have a new experiment, and this experiment does not fit into the existing theory. So this is the first step whenever you try to formulate a new theory, that you have new experiments which challenge the existing theories, right? This is the first step. The second step is that these experiments, which are the new experiments, they guide us. These experiments, they guide us for new postulates. So you start your theory with set of postulates. Then where from you bring these postulates? How do you set up your postulates? You are guided by the experiments to set up the postulates. These are new ideas normally, and in the theory, these are new ideas. These ideas you obtain from experimental settings. And here again, I will give an example. For example, you know that in Rutherford experiment, the electrons go around the nucleus, and nucleus is supposed to be positively charged. So the electrons move around the nucleus, but the classical electrodynamics predicts that if the electron loops around the nucleus, then it will release electromagnetic waves. So it is going to act like an antenna, and the electrons will lose energy. And since they lose energy, the orbit is going to drop in size, and ultimately the electron will collapse into the nucleus. But this does not happen because the atoms are stable. Therefore, Bohr postulated that there exist stationary orbits. So where from he got the idea? He got the idea from the experiments itself. So the experiments are actually the basic things that you start whenever you formulate a new theory. In experiments, you have new challenges. The existing theories don't fit. Then these new experiments that you happen to observe, they guide you to form a set of ideas which we call as postulates. Now, what is a postulate? What do you mean by a postulate? Postulate is something that you cannot prove in that theoretical setting which you are proposing. So postulate, you cannot prove it. You cannot prove it. It is something which is fundamental to theory. It's a fundamental thing. You can't prove it through the theory that you are proposing, right? Because that's how it becomes a postulate. So these are the new ideas. Then how do you know they are right? The only way to prove your postulates is through experiments. So you can only verify that they are right. So there I can also quote an example. For example, you have Newton's laws of motion, okay? There are 3 laws, as we know. 3 laws of motion. Fine. Now you cannot derive these 3 laws within the Newtonian framework. It's not possible. They are the basic postulates and you cannot derive them. All you can do is you test them and experiments prove that they are right. So you can just test them experimentally. So it's postulates are subject to the experiments. And if there is a single experiment that goes against the postulate, any postulate, then the theory will collapse. Theory will collapse even if a single experiment is able to falsify its postulate, right? Then you will have to discard the theory or you may have to modify the theory. Okay, and this is very important thing. Now the question is that we have new experiments, fine. So we have new experimental setting, right? Experimental setting, fine. And that challenges your existing theories, right? New experimental setting challenges your existing theory. Then what do you do? From these new experiments, you figure out the basic ideas that go within these experiments. Those ideas you call as postulates. And these postulates, you cannot prove them. All you can do is that you can verify them through the experiments, right? But is that all? Do we have postulates and we have a theory? No, we don't have a theory just to having postulates. You need one more thing, that is mathematical framework. So you should have a proper mathematical framework, and then these postulates with that mathematical framework can make predictions. So not only can you make predictions, but you can also deduce and you can also address all the experimental results that you have that were baffling you. So that is the idea of proposing postulates. Then you have a mathematical framework on top of that. And when you have postulates with the help of the mathematical framework, the beauty of the theory is that you can make some predictions, you can challenge your experimental colleagues, and you can also address whatever experimental results you are already having, that is the new experimental findings. For example, I give an example, and that's very interesting example. So there were these Kepler's laws. We all know that. These laws were obtained after verifying these data, astronomical data. The data was collected by Tycho Brahe, and he tried to understand the data, Kepler. So Kepler discovered that there are the laws that they follow a pattern. He called them as laws of physics, and we now famously known as Kepler's laws. Newton proposed the postulate F is equal to G m1 m2 by r square. That is the working principle behind these laws. In fact, with this Newtonian proposal, this is the postulate in the theory. Law of gravitation, you cannot prove it. All you can do is you can verify it experimentally whether it fits or not, right? So this was kind of a postulate in theory of gravitation. Then is that all? You have the law of gravity and then you can have the theory of gravity? No, there was problem. There was problem mathematical framework to figure out how the orbits of the planets. And in fact, at that time, there wasn't a mathematical framework available. Newton had to invent a mathematical framework. Now we call that as calculus. So he invented calculus because he needed to make predictions and then use his postulate to address the experiments of that time. So this is how the theory works. So this broadly, this is how every theory works, right? In physics, we have experimental challenges. Then from those experimental challenges, we give a set of axioms or postulates. These postulates cannot be proved. Then you also have a proper mathematical framework. Within these postulates, within that mathematical framework is going to make predictions. And not only that, you are going to address the experimental findings in which from where you actually started. This is how a theory in physics will work normally. Okay, now all these things don't happen in one day. It takes time, right? It happens, a lot of people come and contribute, and there is time when people do these experiments, then people come with different proposals, then we have to see which one is a good proposal. We may have at times to delete some postulates, have some other postulates in the theory. That's how the science works. So this does not take place in one day. There are various proposals, there are different models. So normally you come and we have different models. Sometimes, there is a lot of work to be done, that you have to really choose between the models. You have to figure out which one is the most accurate model, and that model might become a theory. The theory is then a superset of all models. So theory is actually a superset of all models which are proposed to explain some set of experiments. So that's how things work. Okay, and after you have this superset that can entertain all the models and that has refined all the proposals, then at last you have a theory. So you have a, a theoretical framework. So this comes at the final stage, you have a theoretical framework, right? So this also happened with quantum mechanics. We started exactly at 1900, you had experiments, right? And we were not able to understand these experiments. Then we postulated few things. We made some speculation, ideas came up, like you have de Broglie's idea, you have Einstein's idea, you are just improving the things bit by bit, right? So you have different ideas, lots of them. You have Bohr's idea. Then a stage reached where we now figured out that how to all these models, how to take recipe from all the models and build up what's called as our quantum theory. So quantum theory is finally a it is the product of all the things that have been happening in physics for over around 30-40 years. And in 1940s, we had a proper theory of quantum mechanics, which has a proper setting, proper mathematical framework. We have postulates. Within these postulates, then we have mathematical framework. And then we try to address all the experiments that were challenging before we could address those experiments. That's how the quantum theory works, right? So now we are going to go to the proper theoretical framework of quantum mechanics. We'll explain what are its postulates, right? And then what is the mathematical formalism within which those postulates work? And then how do we make predictions? Not only that, how are the experiments that are already known, how they are addressed? Okay, and this is the way, all the theories work in that way only. Okay, so when we present a new theory, when we propose new theory, when we propose new theory, it is possible that the postulates are completely new ideas, nothing to do with the existing theory. So we have complete new ideas, or the postulates are totally fresh postulates. They have no belonging to the earlier existing theory. For example, relativity. In relativity, what do? You propose two postulates, and they have nothing to do with the Newtonian mechanics. But then once you go to the low speed limit, when the speed is very, very small as compared to the speed of light, the Newtonian mechanics will come down. Newtonian mechanics will be obtained as limiting case. So But the postulates of the relativity are totally independent of Newtonian mechanics. They have nothing to do. You develop relativity totally independently, but Newtonian mechanics comes as a limiting case from relativity. But this is not the way quantum theory works. Most of the time, theories work that way only. You have new postulates, new ideas, then the old existing theories come as limiting cases out of the new theory. But quantum mechanics does not work that way. Quantum mechanics does not work that way. It does not work that way. What is that? In what way it works? You need classical mechanics. You need classical mechanics to formulate a quantum theory, right? So without the ingredients from classical, without the ideas of classical mechanics, one cannot develop quantum mechanics. And then, of course, you can also get classical mechanics as limiting case of quantum theory. So this is how the theory is formulated. Since we need classical mechanics to formulate a quantum theory, therefore, in order to give your postulates, in order to give postulates of the quantum mechanics, we'll have to visit a bit to the classical domain, and then we will propose the postulates of quantum mechanics. Now, a classical system, is defined if you have fixed position, say initial position and initial velocity or momentum. So one and the same thing. So if you fix position and momentum of a classical system, then we say the state of the system is completely determined. State of the system is fixed. System is completely defined. Completely defined. Okay, so state of a classical system is completely defined if we fix position and velocity. So then how do these positions and velocities change? Will depend upon what is happening to the system. It depends on in what kind of framework there are various ways of finding out position and velocity final, or final position and final momentum. There are three approaches to do a classical problem. You can have Newtonian mechanics, right? You can use that approach. You can use Lagrangian dynamics, or you can use Hamiltonian mechanics. These are three different recipes for addressing actually the same kind of problem. Then how do you define what happens to a classical system? You define a phase space, which is the space of momentum and position. A point in the phase space represents the state of the system. Now, as the forces act on the body, or as the system evolves in time, the point will move and define a trajectory in phase space. And what is going to happen, each and every point can be determined, provided you have a knowledge of force or Hamiltonian or Lagrangian. That's how classical mechanics problem is solved, right? And how do we beautifully go from classical to quantum domain? We use Hamiltonian mechanics, right? That is in first quantization technique, we smoothly go from classical to quantum through this Hamiltonian formalism. So that's why we'll be only discussing Hamiltonian equations. And so these are called Hamiltonian equations, right? So dq by dt is del h by del pj, and del p, it's momentum, differentiation with respect to momentum, and that rate of change of momentum is minus del h by del qi, where pqi and pj, they are the canonically conjugate coordinates. So they are the dynamical variables, some sort of positions and velocities in the system. So as I know the initial position and initial velocity, at any instant I can find position and velocity through these equations. Then any physical quantity, any dynamical variable is the function of the position and momentum. So that means once I understand, once I solve the equations, I find position and momentum at any instant, I can know the complete dynamics of the system, because every other physical quantity, it would be the function of position and momentum. This is how the classical domain works, that you define the state of a system by a point in phase space, and as time evolves, there will be a phase trajectory, and that trajectory would depend on how the system evolves in time. Now, this whole idea would collapse in quantum mechanics, because in quantum mechanics, there's a basic idea about uncertainty. That means that we cannot find position and momentum simultaneously. If we cannot find position and momentum simultaneously, therefore the same method cannot be used to fix the state of a system. So position and momentum at one moment are not known precisely. Therefore, classical method cannot be used to find the state, to define the state of a system. Now, how do we define the state of the system? What is the meaning of dynamical variables in quantum mechanics? How system evolves in time? For these, there are the set of ideas which we call as postulates. So now we will introduce the postulates of quantum theory. The first postulate is the postulate of a state of a system. What does it say? That a quantum mechanical state is defined through a wave function, psi xt, right? And this wave function contains all the information about the system. This is our postulate, fine. And how do you represent in mathematical form? What is the mathematical formalism of the wave function? It is defined by, it is denoted by this kind of a vector. This is actually in Dirac notation, it's called a ket vector. It's a vector in some sort of a mathematical space, which we call as Hilbert space. These are actually mathematical terms. Now, what do we mean by Hilbert space? There are a set of axioms which the vectors, which the functions need to satisfy in order to be a part of the Hilbert space. So we say that that wave function defined as a system completely contains all the information about the system, and this wave function is represented as, it contains all the information, and it is actually a part of, it is represented as a ket vector, as a vector, as a state vector. So it's a state vector in space we call as mathematical space, that's called as Hilbert space. Most of the mathematical formalism of the quantum mechanics happens to be within what's called as Hilbert space, right? So remember also that if psi is a wave function, then psi1, psi2, psi3, these could be the elements of the vector space. Then their suppose psi1 and psi2 are two wave functions, their sum is also a legitimate wave function. Now, which wave function is legitimate, which wave function is not legitimate? We already know that what should be the constraints on the wave function. It has to be continuous. This derivative has to be continuous. It has to, its psi star must exist, and that it should converge. So those things then go in within this postulate only. There is no new postulate for that, right? So all the first postulate, if I summarize it, it is that state of any physical system is the state of any physical is specified at any time by a state vector in Hilbert space, right? And it contains all the information about the system. Superposition of a state vector is also a state vector. So very nice. So now we have, postulate number 2. Postulate 2 is actually called the quantization technique. What it says that in classical mechanics, you have physically observable quantities, which we call as physical quantities, like position, momentum, you have kinetic energy, total energy, angular momentum, and other physical quantities. In quantum mechanics, we elevate these physical quantities to operators. They are replaced by their corresponding operators. So this is a postulate in quantum theory, that observables and operator postulate is the postulate number 2, that every physical quantity in classical mechanics is actually a Hermitian operator. What do we mean by Hermitian operator? It is an operator that has real eigenvalues, and we'll talk about these technical terms, eigenvalues and eigenvectors and all these things. But what you should understand from the second postulate is that the dynamical observables, that the physical quantities that we happen to know in classical mechanics, they are converted into operators. And the scheme of converting these physical quantities into operators, that is called quantization. So actually, this kind of quantization is called first quantization. Then quantization. Okay, then there is something called a second quantization, where you take wave functions and quantize them. That would be a second level of quantization that you do in field theory. But here, the first level of quantization is that we take these dynamical observables and you quantize them quantize them means you convert them into their corresponding operators. And we know how position is represented through an operator, how momentum is represented by an operator. We've already done this in our previous lectures. Then all other physical quantities being functions of position and momentum can easily be expressed in terms of operators. So let me read now the second postulate. To every physically measurable quantity A called a observable or a dynamical variable, there corresponds a linear Hermitian operator whose eigenvectors form a complete set. And this is important, right? So this would come in also as in measurement postulate, that whenever you operate this operator on a wave function, it returns the eigenvalue. And that would come in our next postulate. Okay, this is our postulate third. And here, this picture of cat that you have been seeing in my all slides, I will try to explain it. This is called the measurement postulate, or the measurements and the eigenvalues of an operator. You see, in a quantum mechanical system, the wave function defines completely the state of the system. It contains all the information, and this wave function could actually contain many wave functions, right? So it's possible that this wave function is sum of many wave functions. These are all, this forms a complete set. So the wave function is actually, and now it has many wave functions, and we call them as, say, eigenfunctions. Now, when you operate an operator on a wave function, then it will give a value and it will collapse the wave function in that very state. So it will give an eigenvalue corresponding to that eigenfunction. So this you need to understand a bit, right? So this is the postulate, what it tells, that operator operates on a wave function, returns the eigenvalue and eigenfunction of the system. What do we mean by this eigenvalue and eigenfunction? What does it technically mean? So basically, a quantum mechanical state could be in a superposition state. For example, you have a cat, and the cat, this is cat, okay, and it is in a box, fine. The cat is inside a box, and in that box we have a poisonous gas, there is a pot which contains poisonous gas, and there is a hammer. You can see this hammer is there, and there is a radioactive material that can emit an alpha particle, say, and trigger a Geiger counter, and Geiger counter is connected with these rods, and once there's a mechanical system, it gets triggered, hammer breaks the pot, releases the gas, and the cat dies. Now the question is asked, if you don't look inside this box, is cat alive or dead? Right. Now, the phenomena of radioactivity is a probabilistic phenomena. Say there is one radium atom, right? And whether it will decay or not, you don't know, because you have a half-life, you don't have a full life. It is possible that radioactive atom has decayed. It's also possible that radioactive atom has not decayed. So you ask a question to a person outside the box that, can you tell me the cat is alive or dead? A quantum mechanical answer would be that the cat wave function is the superposition of dead and alive cat. Right. So as long as we don't see into the box, the cat is both dead and alive. The moment you see into the box, now what is happening? You have made an experimental observation. When you make an experimental observation, the cat would be either dead or alive. So he will choose to be in one of the possible eigenstates, right? So when you look into the box, it is that time when you decide what you want to see. So it is that time when the cat wave function would collapse, either in a dead cat wave function, or the alive cat wave function. So the observer decides, observer affects the entire system. And this goes in the heart of quantum mechanics, that when an observation is made, when that observation, how do you represent that mathematically? Mathematically, we represent it by that an operator operates on the wave function, then it collapses the wave function in one of the eigenstates. And once the wave function is collapsed, another observation is not going to do anything. It will remain in that state. And it's going to remain. Say, suppose once you found the cat is dead, another observation won't make cat alive. The cat is dead because the wave function has collapsed. So technically, we call it the wave function has collapsed. Okay, then we have this, the fourth postulate, which is the probabilistic outcome of a measurement. Since we know that wave function, it's complex in nature, it's complex in general, and it contains all the information. The dynamical variables, we know they are now operators, and once an operator operates on a wave function, right, it collapses the wave function in one of the eigenvalues. If then we have what's called as eigenvalue equation. Now the question is that what does wave function, how do you, the question is, what is the physical interpretation of wave function? I told you there is some, what was as Max Born postulate, that wave function can be interpreted as wave function we know has no meaning, but modulus this square of the wave function is the probability density. This is what we discussed in our earlier lectures. It is the psi star that represents the probability of occurrence of the particle between, say, x and x plus dx. So it gives the probability outcome of a result, right? So the probability outcome of any result can be then be postulated in terms of the expectation values, which we have introduced in our previous lecture. So the point here is that the postulate 4 is about the probabilistic outcome of a measurement, because we have the probability interpretation of the wave function. This probability interpretation goes as one of the postulates, and further the postulate of this what we call as expectation value is contained here. So then we have two kinds of spectra. You may have observable that has discrete spectrum. For example, energy levels in harmonic oscillator are discrete, right? Or you may have a variable which is continuous, like the position variable is continuous. So we can either have a continuous spectra or a discrete spectra. Say energy of a free particle is continuous, whereas energy of a bound particle is discrete. And this is how you define it. You figure out this psi is actually psi star psi d tau between minus infinity to plus infinity. And normally, if it is not there, this could be 1, because we can choose a normalized wave function. And we know how to define expectation value of x. So expectation value of position is minus infinity to plus infinity, and then psi star, the operator psi, this is how you normally represent it, and d tau. And then if it's a normalized wave function, you will have 1 here. Again, you define the expectation of value of the momentum. Momentum in configuration space would be that it is psi star minus ih bar del by del x of, and then psi d tau whatever, or dx, because this is one dimensional, so dx. And then we can find expectation value of any other operator, because once you know how to write down position and momentum as their operators, then we know how to find, because there is a postulate for that every dynamical variable is replaced by the operators. And keep it in mind that expectation value is not like classical average. In classical mechanics, how do you take an average? I already told it in my previous lecture that you take repeated measurement of an experiment, but that you cannot do in quantum mechanics, because every measurement is going to affect the system. So in quantum mechanics, the average mean is that you have n copies of the same setting, and then you make observation on all the n copies simultaneously. The average value there is called the expectation value. So that goes as the postulate number 4, which we call as the probability postulate, and we also define expectation values through that postulate. Then we have the last one is the Schrodinger equation. Schrodinger equation itself is the postulate of quantum mechanics. It tells me that if a wave function is given to me now, I can find the wave function later. So it's called the time evolution postulate. This tells you that ih bar del of psi by del t. It tells you how the wave function evolves with time. Tell me what the Hamiltonian operator is, and then I will solve this partial differential equation to tell you what the wave function would be at any later instant of time. So this was these were the sum of these were the postulates, the all 5 postulates. I have discussed it with you. In the light of these postulates, do we develop the quantum theory? So do we need only postulates? Yeah. We don't need only postulates. We also need a mathematical framework, and that mathematical framework has a nice setting. We use linear algebra, and we use what's called as Hilbert space, And there are many approaches to how people have different approaches when it comes to the mathematical formalism. There's a matrix mechanics approach, and then we have this vector state vector approach, and then you have all sorts of these beautiful mathematical frameworks. And but then we can always prove that all these frameworks give the same results. So this was our today's lecture. It was only targeted for these postulates in quantum mechanics, and I hope that now you understand. In next lecture, we'll talk about the connection, and we'll try to get classical mechanics as a limiting case of quantum mechanics. So that would be in our lecture 8. This is our lecture 7. So this is the wrong slide here. Lecture 7 has concluded now. I hope you enjoyed the lecture. Please give me your comments about the lecture. And if there are any scope of improvement, I would be very happy to receive your comments. Thank you very much.